Okay, now we want to know how we can get this equation. Alright, so we know how to get the first two component. So the third component for the uh, damper, the 2 zeta omega n can be obtained actually from this equation. So we divide everything with m, so we get this equation, right? And we can see that the coefficient for x dot is c over m. So we multiply with this fraction. Right. After we multiply with that, and we go to the next slide. This is the formula for zeta. So we replace zeta. We substitute inside the coefficient, so we get this one. Right. So that's why we have 2 zeta omega n right here. So you just need to remember that this is the formula for zeta, which is the viscous damping factor, and it measures the severity of damping. And now if we want to solve equation of motion for damp free vibration, from this equation we want to find the equation for displacement alone without the x dot x double dot. So this is the solution that we can assume, and from here we can okay, how we get this equation is based on mathematical solution. You have learned this in maths 2, so I don't have to explain it right here. So we find x dot. So how to calculate x dot is we differentiate it. So we have a lambda e lambda t. So x double dot is equal to a lambda square e lambda t. Simple. So we substitute everything back to this equation. So we will get this. We can eliminate the exponential component, and also a, because every part of this, every component has the same constant a and also exponential. So what left is the lambda. So we have lambda square right here, lambda here, right? So this is the equation, and it looks like a quadratic equation, so we can solve it. So we use the quadratic formula to find the root for the lambda in this equation. So we use the root of the quadratic equation. So we get that the first root is this one, and also the second root. So notice the difference is plus and minus. Actually, you still remember this quadratic equation. So since linear system have the property of superposition, which means that the general solution is the sum of the individual solution. So each correspond to one root of the characteristic equation. So since it is superposition, property of superposition, so we can add both solution, both roots. I mean, in term of the in this form. So we put the root we get, which is lambda 1 and lambda 2 right here in the lambda over there. and then we add both of them. So this is the outcome, and the constant is different. So this is the general solution, and when we put the value for the root here and also right here, we will get this one. Alright, so this is the general solution for the damp-free vibration. Okay, so this is the case if we get two different root, but what if we get similar root, one similar root, or what if we get complex root? So remember, quadratic, sometimes we can get this kind of shape where there is two root. Sometimes we can get one root. This sometimes we can get complex root where there is no intersection. Okay. So when we consider the root, if we get the one single root, no, in this case actually this is wrong. Okay, for the overdamp situation, or this is the categories of damp motion. So for overdamp, actually the root that we can find is actually we have two root right here. So this is overdamp situation. We have root lambda 1, lambda 2. Okay, they are distinct, different real and negative numbers. So the motion decays so that x approaches 0 for large values of time. Okay, large value of time. There is no oscillation and therefore no period associated with the motion. So if you want to look at how is overdamp curve is right here. Right. So it takes a long time to damp the system. So we call it overdamp. We have another category of damp motion, which is a critically damp or critical damper. We can see that, where the zeta is equal to 1. Previously, the zeta is bigger than 1. So that is the importance of zeta. From there, we can see whether the system is overdamped, critically damped, or underdamped. The third category is underdamped. So in the critically damped, the roots lambda 1 and lambda 2 are equal. Both are real and negative numbers. So this is the root. So the solution to the differential equation for this special case is right here. So you can remember this formula. So for overdamped category, the formula is given previously, and right now is the critically damped. So in this case, the motion decay with x approaching 0 for large time, but not so large compared to overdamped, and the motion is again non-periodic, non-oscillating motion. A critically damped system, when excited with an initial velocity or displacement, or both, will approach equilibrium faster than will an overdamped system. So this is the fastest this is the fastest the motion can be damped for a particular system. So each system has its own critical damper, and this is the fastest. And we cannot go faster than this. Alright. So if we lower the damper, we will get under damp category, and we sometimes we don't want under damp category, because I will show you after this what is under damp category. So now we go to the under damp, where the zeta is lower than 1 and it has oscillation. So that's why we don't want under damp category, but sometimes it is useful. So in this under damp category, we have this kind of quadratic, where we have no real solution, we have no real roots, and what we have is complex root, two complex root. So this is the formula for under damp, or actually the solution, the general solution for under damp. So it's quite long equation. So this is actually we just replace the lambda with the solution right here. This is the solution for the quadratic calculation. Okay, and we can use Euler formula. So when it is positive, it will be positive, but if it's negative, we can put negative sign right there. And this is the outcome. If we use Euler formula in this equation, and this will be the outcome. So it's a long way to how to get this equation, and we have two constant, so x and psi. So x is the amplitude and psi is the phase difference. So for the under damp, if so when we get this equation already, we can get the, this is similar for any case like over damp or critically damp. If we know the initial condition where when time is 0, so what is x and what is x dot, so from here we can get the the constant, the value of the constants, x and psi. So we can just put the value, replace the t, and we can get the constant. So the equation represent an exponentially decreasing harmonic function for specific numerical values. So the frequency, actually we can replace this component with w or omega d. So omega d is equal to omega n multiplied with sert 1 minus zeta square. So this is equal to this one. And this is called the damped natural frequency. So we have natural frequency, and if we have damper, we can calculate the damped natural frequency. Alright. So this is the behavior of under damp. So when we call it underdamped, it means the damper is not enough. And that's why we still have oscillating motion in the motion of the in the displacement. And anyway, in the end, it will damp the motion, and the motion will stop. Okay, so in this case, we know the initial condition. At time 0, we have displacement equal to 30 millimeter and the speed is equal to 0. Alright, so we can calculate the value of C right here. Alright, C is similar to X in this case. Alright. So how to determine damping by experiment? So we often need to experimentally determine the value of damping ratio zeta for an undamped system. Okay, so for undamped system, usually of course it will still have some damper, the unintentionally damper, so we can calculate it. The usual reason is that the value of the viscous damping coefficient C is not otherwise well known. So that's why we need to sometimes when there is no dashpot in the system and it still has friction, so we want to know the damping, so we can do experiment. To determine the damping, we may excite the system by initial condition. So like a beam attached to the wall, so we can do the vibration, we can displace the end of the beam, and we can see how long it will take for the beam to stop. So from there we can calculate the damper, the damping ratio zeta. So from in the experiment, we can obtain a plot of displacement x versus time t. So this is example of the plot. So we can get the first from the plot. This is the simplified shape. You can shape like this. So we can get the first peak, and we can find the second peak. We measure the displacement. Okay, so for example, this the displacement is x1 and the second one is x2, similar to this one, x1 x2, right? So this is the length between the two peak is the period tau. So we can calculate tau, and tau is actually calculate is related to the damp natural frequency. This is not the normal period, but period for damp situation. And this is the equation that we use. Okay, so again this is similar to the psi, and this is similar to the big X. All right, so from here we can calculate the zeta. We want to calculate the zeta. That is the how we define the damping in a system. So how to calculate this is actually we can find delta. So delta is logarithmic decrement, and this is the formula ln x1 over x2. So x1 and x2 we can get from the experiment, and this is actually equal to this one, the equation which contains zeta. So we rearrange it. We can calculate zeta. So zeta is, this is the formula for zeta, and we can use this formula to get zeta from experiment, and from there we can know the damping coefficient zeta for the particular system in the experiment. Alright. Now we have finished. Now next we are going to enter an example.